We're still missing a few people. Should we wait for a few minutes before we start? All of you had a comfortable stay? Yes, no? How many commuters do we have? Those who are commuting every day? Oh, yeah, we do have. I'm surprised. Okay. Otherwise, hostels, okay? Okay. Right. I think I'll get started, kick off today's lecture. In fact, yesterday we had a few sessions on rheology. So we introduced to you what rheology is all about, and that was from the perspective of cement paste, where we're looking at cement paste as a fluid, right? And at that stage, then we are not exactly separating out cement paste and looking at constituents. So we say cement paste is like one continuum, right? So it's like one fluid, and we try to assess its behavior when we shear it, because flow is all about shear. You cannot induce flow unless you shear any fluid, right? A fluid will flow only when you shear it. So we need to understand how a fluid flows under applied shear, right? Now, shear is a generic term. Shear can be a force or a stress, right? And oftentimes we have control over the force part of it. We do not have control over the stress. Stress is something that is generated internally inside a material, whether it's a solid or a fluid. A stress is generated inside. We can visualize stress as if it is a resistance of any material, right? If it is a solid, it will be resistance to a shear strain. So what happens when you apply a shear strain to a solid? It will deform and it will come to a rest, right? It will come to rest in a deformed state. And we treat that as if it's a quasi-static or a static problem. That's how, and basically the entire field of elasticity, as we call it, builds on that concept. And then we go on further to get into structural mechanics, where we do analysis of complicated structures and all these things. But the fundamental premise there is statics. The object is at rest, it's not moving. So what is the independent variable there? The strain, right? And what is the stress? It is the resistance that is generated from inside the material. And directly measuring stress is very difficult, right? So what do? When we're doing measurements, we have a control on the force, right? We can measure the force and we can measure the deformation. What do? We somehow infer the state of stress. Infer. Even when we are doing a simple static test like a tension test on a steel bar, we only have control on the force. We don't know what is the state of stress inside the material. We infer it. We make certain assumptions, right? What assumptions do we make? Suppose I take a steel rod and I do a tension test on it. What assumptions do we make? We assume that the stress is uniform across the cross section. Fundamental assumption. Has anybody bothered to check it? No, it's an assumption. Under that assumption, we derive the state of stress even for a solid. Same thing applies for the fluid also. I have control on the torque. That torque generates a shear stress in the fluid. What I try and do is try and create, as far as possible, idealistic or ideal boundary conditions so that I can create an idealized stress state in the fluid, right? Now, in the case of a fluid, when I apply a shear stress to it, what's going to happen? I'll produce flow, which means I'm not limited to strain only. What I start generating is a strain rate. It starts shearing and it continuously shears, right? So how did we measure continuous strain deformation of a fluid? Strain rate. That tells me how it is deforming, right? It's a dynamic state now. So that relationship between the shear strain rate and the shear stress is what we are looking for when we are trying to do the rheological characterization of a fluid. That is the essence of rheology, trying to understand how a fluid responds to a strain rate. right? And that was what last lecture was all about. Now what we are trying to do is to build up. We're trying to build up, knowing this information, how do we proportion concrete? So we're now going to the next scale, right? And so what is the next scale? Now aggregate come into the picture. And I think in the last lecture, Narayanan kind of left you in a very titillated position where he said, oh, I'm going to put some aggregate and then we'll create packing with this thing. So that's the essence of it. The minute you introduce aggregate, there one has to be a reason why you introduce aggregate. Okay. The second thing is we have to deal with the consequences of bringing in aggregate. Okay. So let's deal with this. Let's first try and understand how we've been doing it for regular concrete. And then, of course, once you get into 3D concrete printing, once we understand the causal links here, and they're embedded in our code, whether we believe it or not, then we extend it to the case of developing concrete mixtures for 3D concrete printing, right? So just again to recap, from rheology perspective of a cement paste, we understood that we have a Newtonian fluid, right? What is a Newtonian fluid? We said the stress, right, is directly proportional to the strain rate. That means if I try to deform it faster, the fluid will give me a higher resistance. Fundamentals of a Newtonian fluid. Then the next level of complication is when you have a fluid that has a yield stress. So what happens there then? If you look at the plot between gamma dot, which is the strain rate, and tau, which is the shear stress, it's a straight line that starts at origin for the case of Newtonian fluid. The minute I introduce yield stress, what happens? That curve shifts upwards. You get an intercept. What is that intercept? That is the yield stress. Why is the yield stress happening in this fluid? It's happening because there is something inside the fluid that is giving us a resistance to shear. When I apply some shearing to this fluid, internally there is some structure that is resisting it. Okay, and I have to overcome that structure to produce flow. Now, that resistance that the fluid gives to initiating the flow is what we are calling yield stress. Now, the question is, how do we measure it? To measure it, I have to use some protocol. Whether I call it a constant strain protocol, constant strain rate protocol, or a strain rate ramp, there are different protocols. And then it's all about inferring what the liquid is up to, what the fluid is up to, right? So now, well, that was all about paste, and now we're talking about concrete. The minute we come into concrete, this is a picture I've shamelessly stolen from the web. So this is typically what a concrete looks like, right? So we know that we have coarse aggregate, we have fine aggregate, and of course cement, water, and some admixtures. The proportions of this is what we are basically interested in when we are trying to proportion our concrete, right? So now, what does concrete look like? If you want the real technical description of concrete, this is what we are trying to describe, right? If somebody was to look at it, one is that it's a bit of a stretch if you were to call this a fluid. It doesn't look like a fluid in any sense of the word, right? But it behaves like a fluid. I mean, look at this. Would you call it a fluid? Because our sense of our imagination about a fluid is something that looks smooth, it's continuous, right? Applying those principles here is a bit of a stretch, but it behaves like a fluid, right? It flows. As you can see here, there's concrete being dumped off a chute, right? And it's flowing. So therefore, we say it's a fluid. But it's actually a very complex heterogeneous suspension, right? What is the suspension? When you have solid particles which are suspended in a fluid medium. That is a simplistic definition of a suspension, right? So, and that itself you'll see will become very complex once you get into concrete and trying to proportion it. So for now, we'll just simply stick to this definition where we say it's a complex heterogeneous suspension. Heterogeneous because there are different types of particles. It's not just one type of particle that we have there. So of aggregate of different sizes in a paste, which is basically cement paste or a cementitious paste, okay, which basically is my fluid medium. Even that definition becomes complex because what do you call a fluid? We'll just see in the next slide is itself not very clear. So at some level of idealization, if I was to look at it, I could look at concrete, which is shown here. As if I have a fluid medium, which is at some level I can call it as a paste. That is the fluid medium. And basically, when we talk about a fluid, we immediately think of rheology, right? So the rheology of the fluid is, if I was to ask you, can you give me the property of a fluid? Your first question would be, which rheological property would you want me to give you? Because we're talking a fluid. Therefore, if I look at this as my concrete, I can separate out the paste and the aggregate. I can separate out two phases in there, right? The so-called fluid phase, which has a certain rheological component or which has a rheological behavior, and that is my fluid component. Then I have the solid component, which is the aggregate, which basically serves as the filler, is basically filling the space in there. And each component has a role to play in there, as we'll explore. When it comes to the aggregate, the two things that I will be looking at least in a concrete proportioning, will be the content of aggregate. How much aggregate do I have in the concrete mix? And the packing. This plays a very important role. I'll just touch upon packing, introduce to you packing. I think next few lectures are going to be heavy hitting on packing, where you'll get into the deep end of packing. I'll just merely introduce what packing is all about. So, what is it that we are proportioning a concrete mixture for? We're basically trying to come up with the proportions of these components, the fluid component and the solid component. How much should the fluid be? How much should the solid be? Right? And what is the purpose? Well, we're trying to achieve concrete with a certain strength and durability, workability and flow characteristics, and ultimately economy. I want to save money at the end of the day, right? These are my threefold objectives with which I try to develop the concrete mix designs. And for in India, we follow this IS 10262, which is our base code. It's been revised, that I remember, twice. Now, of course, we have this in the bilingual format, which I find rather confusing, but it is available in the bilingual format now. And this gives us the general guidelines. And what I want to do today is look at these guidelines that are available in IS 10262 and understand the basics of it. And believe it or not, a lot of these guidelines that have come into this code come from fundamental ideas of packing and what we understand about cement hydration and cement rheology. Okay, except they're stated in a layman language because they don't expect everybody or a practicing engineer to be understanding the concepts of packing or rheology. So they're framed in such a way that thou shalt, that you will do this, right? And in doing so, they hope that some basics are covered. And what are our objectives in doing the concrete mix design? Strength and durability, workability or flow, and economy. Now, let's hit the strength component. So, if you read IS 10262, you'll find this generic statement where they cover all bases. They say, well, look, strength of concrete depends upon all of these factors. It depends upon cement, supplementary cementitious materials, the aggregate, maximum size and grading, surface texture of aggregate, and whole bunch. That notwithstanding, right, the most important characteristic that defines the strength of concrete is the water to cement or water to cementitious material, the ratio of that. And we all know, if I reduce the water to cementitious material, my strength goes up. But what is the consequence of that? If I was to reduce the water to cement ratio, let's just keep it at water to cement as my cementitious material, what would happen? Suppose I decide on a certain proportion of paste and aggregate. Right? If I decrease my water to cementitious material or water to cement material, what would happen? Now, my cement content in the concrete would go up, right? Because the proportion, I'm fixing them by masses. Let's say I say 40% of the concrete is going to be paste, 60% is aggregate. Now, what defines the cement content in this 40% of the paste is the water to cement ratio. If the water to cement ratio is low, cement content in the concrete will go up. Two things happen because of that. What are two things that happen because of that? My cost goes up. There are no free lunches. When I try to do something, something else goes wrong. So what happens when the cement content goes up? My economy goes for a toss. So unless I have a really good reason, I'm not going to do it. Right? What is the other thing? The other thing is that the rheology of the paste depends upon water to cement ratio. So my workability will take a hit. We have to expect both of these things to happen. But fundamentally now, this is the graph that is available in IS 10262, which relates the water to cement ratio to the strength. And we know it's an inverse proportion. This is now actually given in 10262. They give it as a master curve with enough riders there saying that you have to test this and establish this curve for your own for your own cement type, right? But generic behavior is this, that we expect that we would see a decrease in the strength with the water to cement ratio. That's expected from this the cement paste. But please remember that if I start going up this curve in the hope of achieving more strength, I'm doing two things. I'm increasing the cement content, and at the same time I'm making my paste thicker, more viscous, yield stress increases, and all the wonderful things that happen because of that. So now let's explore what happens when we start tinkering with these and what other levers do I have. So when you're trying to do a mixed design, you have a few levers in your hands, right? When all else fails, we'll say, fine, now I have this. Now let me bring in some admixtures. That is the role of admixtures. Admixtures are basically there that say, okay, I played with my fundamental components, cement, water, and aggregate. Okay, I'm now stuck with this because I've hit two of the three boxes, right? The third box, now how do I manage the third box, right? So at some point you'll find that you cannot manage all three boxes with just water, cement, and aggregate. So I need some other lever. That's where the admixtures come in. So what would we expect from an admixture? It is something that I would use in a very small quantity so that the basic proportioning does not get upset. I've already done that. Now, if I start introducing a third component, which starts playing around with my basic composition, then everything else changes. So it has to be used in such a small proportion that it doesn't upset what I've done with my basic proportioning. And it introduces some change in the behavior or modifies the property some way, which I can't do just with the basic proportioning. Okay, so admixtures are my last resort. Okay, which is the last lever that I have in order to tick all three boxes. Okay, right. Now, so we said strength, we've looked at it. Water to cement ratio is my primary lever that I'm going to press. The second thing is the durability. My concrete has to be durable. Okay, for this, there are provisions that are given in IS 456, which is the parent document for reinforced concrete design. There are a few provisions that are tucked away in here, which basically help guide you when it comes to assessing the issue of durability, right? Now, what are the durability concerns that we have? If you go to 456, which is there is a 8-point, the early sections in there, deals with concrete mix proportioning. And there, we talk about exposure conditions, right? So there are different exposure conditions that are listed that go from mild to extreme. I'm presuming everybody is familiar with this, right? Based on that, a certain maximum free water to cement ratio is prescribed, right? So basically, durability is somehow tagged to this water to cement ratio. The understanding is that if you look at what makes cement paste denser, you reduce the water to cement ratio. What you get is something that is less porous, right? And that will basically prevent ingress of the deleterious materials, which could be chloride ions or sulfates from outside. So if you're looking at durability concern for concrete, the primary concern is to keep the external agents outside, not let them enter into concrete. How can I do that? Well, aggregate at some level are inert. They're not going to allow things to get in. How will things get in? Through the cement paste medium that is in the concrete. How do you control that? With the water to cement ratio. So this is prescribed. It's prescriptive. Okay. They say that we suggest this free water to cement ratio should be capped. And you see that when you go from mild to extreme, the free water to cement ratio that they cap at decreases. Two things happening there. When I decrease the water to cement ratio, what happens? Cement content increases. Okay. And the hardened cement paste would be less porous. That is our understanding. Okay. So that is the basis of durability and mixed proportioning, considering durability when we're talking about concrete mix design. So here what you have to do is, if you're bringing in durability concerns, you look at the parent document IS 10262 and use it in conjunction with IS 456, which basically combined gives you a measure of durability. There's another very important measure that oftentimes is overlooked about durability. Now, like I mentioned, there are no free lunches. If you keep on increasing your cement content, there are other things that happen. It's not just that my cost goes up. or if my water to cement ratio decreases, that the paste becomes thicker, it becomes more viscous, it has more yield stress. Of course, these are all consequences that we deal with, that to live with. But more importantly, what happens is, if you start increasing your cement content, the paste would shrink more. It would produce a lot more heat. These would then produce unintended consequences of cracking because of shrinkage, because of thermal effects, right? So how does our code handle that? They prescribe a limit of 450 kgs per cubic meter of cement in the concrete mix. They say, look, this is a limit, okay? If you go beyond this, then expect that you will increase the risk of cracking. That's what they say. So it's a commonsensical provision which addresses that durability issue when it comes to concrete, right? So these are all things that are already inbuilt in our codes, and most of these are prescriptive in nature, where we're putting limits. We're saying you will not do this, okay? At the core of it, at the background of it, is this fact that we expect, if you start increasing your cement content beyond 450 kgs per cubic meter, expect heavy cracking in concrete because of shrinkage, and it happens, okay? Now, so that is as far as how we've addressed the strength issue and the durability issues in our mix design, the first box, right? Now, the next two boxes. The next box is the one that's actually quite tricky when we start getting into workability, okay? Now, workability, fluid flow behavior, we need to understand what are these, right? What is workability? Well, this is the technical description of it, which basically says that for a concrete defined as a composite, the characteristic that is indicative of the ease with which mass plastic material, that means at some level, it is not that it is made of plastic, but the behavior is plastic. That means if I actually was to somehow force it to move, it would still move. Okay, this goes to the definition of concrete as defined being plastic or solid. Okay, when we say concrete is plastic, at some level we expect it to be a fluid when it is forced to flow, and that when it is deposited in its final position, it is able to conform to the final the fine forming detail. What is implied by that? Suppose I put concrete in a rectangular box. I expect concrete to fill every corner of that box. It has to flow, fill that. That is how I define my workability. If it doesn't fill by itself, well, if I force it, then it should fill. Okay. Now, how do we, if we were to look at it alternatively, what would be the alternative description of it? What we're looking at is the work or the energy that would be required to fill a form. How much energy do I have to put into this material to get it to conform, conform here? How much energy do I have to get to put into this concrete to make it conform, right, with my requirement? And conformity with my requirement is the entire form should be filled up thoroughly, completely, without any air gaps, right? Now, how do we measure flow? Well, the most common measure is this slump. That's what we all use. We are all very familiar with this. But remember one thing, please, that slump is a static measure. What do? We fill a cone, we lift the cone, we let it come to rest. It is a static measure. It, in a sense, doesn't really tell us anything about the flow behavior. Why? Because when we are measuring it, it is already in a static state. It is rested. Okay, but what is peculiar about the shape is if you actually contrast this with what you get with water. Suppose I was to do this with water, what would happen? The minute I lift the cone, essentially you would get a flat surface. Water cannot create or cannot sustain these level differences. So what then allows this concrete to have this level differences? The yield stress. Concrete is a material that has yield stress, right? Now, what would be a good measure of workability? I would say that perhaps this is a good measure and a derivative of this that we are using in printing lately, which is actually called the VB test. What we do in here is that we take the cone and of concrete. When you lift the cone, of course, and there is a container here. When you lift the cone, it's not going to fill the container. Then what do? We measure the energy that it takes, right, to make it fill the form, this container, right? So we would actually be vibrating the concrete. When you're vibrating, what are you doing? You're inducing energy. You're putting energy into the concrete, which agitates the concrete, and gets it to flow. And in doing so, it will fill the container. So what do I get from here is actually a measure of work that I'm putting in to get the concrete to conform with my requirement, fill the form, right? Now, what happens when it goes from here to here? It doesn't want to go by itself. And we'll see the reason a little later, but we force it by putting energy in there, right? Now, if concrete is workable, I put less energy into it. If it is not workable, I have to put a lot of energy. It will take a lot of time because I count the seconds that it takes to agitate the material. A lot of work goes into it before I can get it to fill this form. Now, what happens when it goes from here to here, when I'm forcing it to fill the form? At some level, if you think of concrete as made up of aggregate and paste, then the aggregates would move relative to each other. They have to. Because if they stay in the same configuration as they were when they lifted the cone, then there'll be no movement possible. How will the movement happen? When the aggregates are moving relative to each other. Okay, so these aggregates have to move relative to each other. How easily can they move relative to each other? There are, of course, always the causal effects. The causal effects are, you'll say, well, if the aggregate has a high surface area, or if the surface is rough, they will basically stick to each other, they'll not move. Yes, given. That's one characteristic, right? So you have the primary effects which impede the movement, and then you have the secondary effects. So what we have to look at is the primary effect that would prevent this fellow from filling this form, right? Which basically happens when the aggregate move relative to each other. What stops that from happening? And if that effect is something I cannot manipulate with my primary levers of the proportions, then I have to bring in admixtures to facilitate that. Okay. Now, this is the idealization. I'm going to revisit this just for a few minutes. If you look at concrete, I can look at it as if it's made up of aggregate in a fluid medium that is shown in the light gray here. The aggregate is shown in orange. Now, what scale of representation should we use? What should I call this fluid medium? My one choice could be that I consider concrete as an idealization of coarse aggregate in mortar. So what happens then at that scale of idealization, all the oranges here are coarse aggregate. The gray here becomes the mortar. So what happens then? My fluid medium becomes mortar. Why is that important? If I have to get this fellow to flow, the rheology of the fluid medium becomes important. That means then if I'm looking at that scale of idealization, I should have the fluid behavior of mortar in my hands, right? The second level I can also think of is some coarse aggregate, some of the coarse aggregate or some of the fine aggregate that we use become a part of the gray fluid. Okay, and some of the fine aggregate are considered as a part of the orange dots, the aggregate. Now, this is also done. One place where this is done is when we do SCC, self-compacting concrete. Those of you who've done self-compacting concrete know that we pack it with fines. What happens then? We actually take the fines and count it towards a fluid, right? Although they are aggregate, we count them towards a fluid, and the fluid behavior of that fluid medium, which is now paste and some fines, it becomes important in controlling the flow behavior of concrete. And the third and the most generic argument is where all aggregate, right, fine coarse, are sitting in a paste medium. So the gray here now becomes paste and the oranges become all aggregate, which is coarse and fine, right? So this is the primary level of discretization that I can adopt, where basically everything orange is all aggregate, everything gray is paste, cement paste, right? There's also one more level of idealization. I will not get to that here, but that can also be done, where within the cement, I can look at the cement grains and also look at that as solids and treat only as water as my fluid, but then that becomes a little trickier to handle. What I need to do is understand the role of this fluid medium, whatever level of discretization, and the solids in controlling the flow of this material. Okay, and I also have to bring in economy into my concrete. Right. So these are two things that I want to do. How do I control these things? What are the levers in my hand? One is the relative content of fluid. How much fluid medium do I need? Okay. And for now, let's look at just this level of discretization. What do I mean by that? Cement paste is my fluid. All aggregate are my solids. Okay. Now, I'm interested in controlling the flow behavior and also try to adjust the relative content of fluid in this solid medium, and this becomes important. The relative content of the fluid medium, the relative content of the paste becomes important from an economy perspective, because I want to minimize my cement paste in the concrete, right? Now, so let's look at the aggregate. What is it that we expect from our aggregate in concrete? The aggregates are treated as inert fillers. Basically, they are inert fillers. So what is their job? Pack the volume, right? So what am I hoping to achieve with the use of aggregate? Minimize my cement content or paste content, right? That is the primary role of aggregate. What else would I expect from them? I would expect dimensional stability. I want the aggregate themselves to be dimensionally stable, right? Stiffness, toughness, and wear resistance, and all of these properties essentially come from the aggregate. So I need something, some filler that is strong and durable, right? And it should basically be I address this issue where I try to reduce the cement demand. I want to pack my volume with this inert filler as much as possible. Okay, so that I can reduce my cement content, because by its very nature, I expect it to be an inert filler, right? Just packing the volume. And typical concrete, 60 to 80% by volume is aggregate. This is from years of experience, this is where we are headed to. In fact, now we are starting to get this number starting to creep up a little bit more. And economy, of course. Aggregate are cheaper than cement, right? So it makes sense. Use more of the cheaper material, pack the volume, right? Reduce your cement content, okay? And in the process also provide stiffness to the concrete, and strength and toughness. These characteristics would come from aggregate. So now with my first objective, which I want to minimize the cement content, I have to look at this packing. Broadly, how would we look at packing? Suppose I was to pack a unit volume. I pack in solids in there, and I look at the solid volume as a fraction of the total volume. That's what I want to maximize, this packing density, which is basically the solid volume divided by the total volume. If I achieve a larger number, that means I've managed to pack more solids in there. Remember, whatever is not solid in here is basically paste. So if I go to concrete at the basic level of discretization, all the solids here are the aggregate. The light gray here would be paste. If more space is available for light gray, more the paste consumption, concrete becomes more expensive, right? So my objective with this packing would be to play around with the aggregates, decide on how do I maximize my packing density. That is what I'd be after. What are the rules that we typically follow? Well, whenever we do this packing, typically we fall back on these spherical models, okay? Because while they're not practical, nothing in nature is a sphere, right? And when we talk about aggregate, they are all irregularly shaped. Now, so why this? Well, because they help us understand. That is the basis. So if I look at spheres of uniform size and I try to pack a unit volume, maximum packing that's possible is about 74%. That's the Kepler's hypothesis or conjecture. And that comes when you go with a face-centered cubic arrangement. Okay, that's maximum that you can pack. And if you were to take the same spheres and dump it into this cube and do a random packing, that is, try to shake the cube up rather than arrange it in a systematic manner, you would basically be limited to 64%. Which means if I was making concrete with this thing, these spheres, I have to expect to use either 26% paste or 36% paste, okay, by volume, right? Now, how can I improve the situation is when I get into polydisperse spheres. What is a polydisperse sphere? Here we have a mixture of different sized spheres. So we are not using a single sized sphere for a good reason. The reason is that in polydisperse spheres, what do I expect? I want to arrange my spheres in such a way that I step down in sizes. I start with a certain size, start decreasing the sizes with the objective of maximizing my packing efficiency. I want to basically minimize that light gray space that you saw in the previous slide with the objective of reducing the paste content in the concrete. Now, so here, what is the role of the smaller aggregate in this? The largest aggregates would form like a primary structural framework, if you want to think of it, right? And within the gaps of the larger aggregates, you try to fit in your smaller aggregate. So if I now try to play this game, what is important? What is important is I have to have the right sizes in the right proportions, right? If the sizes are off, I cannot achieve good packing. If the proportions are off, I cannot achieve the proper packing. Both have to hit the right numbers, right? So we follow this thing called hierarchical filling. Suppose I was to give you different size spheres. You take the largest one first, hope to pack the gaps with smaller and successively smaller and successively smaller. And you basically try to maximize your packing. And what is important here? The sizes and the proportion of each. So suppose I start with a certain spherical size here. I have several options to fill the gaps, right? Starting with the simple, if I take the simple bubble diagram here, I have several options that are available to pack it up. Now, suppose I take my largest sphere here. I can go with this as my next arrangement, or I can go with this as my next arrangement, and so on. I can basically play around with these spheres. But if the proportions are off, so let's say I look at this particular arrangement here. This is my largest spherical size, followed by this, followed by this. Suppose I have too many of this size particles, what will happen? Packing will not happen smoothly, right? And we'll see a little later, this thing called the loosening effect that comes into play and becomes counterproductive. So what happens then? I have to make sure that my aggregate sizes are all available in the right proportion. And that brings us into this concept of grading. That is, if I have aggregate available in the right sizes, in the right proportions, then I call them as well graded. Now, what do I expect from a well graded aggregate? I expect that these would pack well. Okay. Now, a few other things to remember here, and that is when I'm talking about packing efficiency, I'm trying to maximize my aggregate content. Now, when we're dealing with regular concrete, we do not take it to some crazy height. We just try to leave it at some point so that we can minimize the cement content. But when it comes to some of the specialized concretes, like say UHPC, we take it to an extreme where we pay a lot of attention to packing. We pack it down to the micron and submicron scale. Here we restrict ourselves to packing up to perhaps some millimeter level scale. But two important things to remember is, suppose and this is just a numerical example, which is very simplistic, to explain two things. One is, suppose I start with a square and try to pack it with circles. Right? It is not at all realistic in a real sense, but helps understand the concept. And the concept is, am I better off starting with a larger sphere initially and then pack the spaces between these with smaller sized aggregate, or start with a smaller size to start with? Where would I get a better packing efficiency? Now, heuristically, you can understand from here that you're better off starting with a larger size. If your initial diameter is large, you can actually achieve a better packing efficiency, because the larger sizes would basically create a skeleton with larger sizes, which I could then subsequently pack with smaller sizes. But of course, grading is very important. But here the role of the larger aggregate size is important in achieving the larger packing of aggregate, larger packing efficiency or higher packing efficiency. The other thing is, what happens when I increase the diameter of a sphere? Well, the volume of the sphere scales as d cube, right? Whereas the area scales as d square. So when I go from here, say, and come to this point here, what have I done? Even if the volume was same for these light blue circles, what has happened for this fellow? The surface area decreases, right? So when I deal with larger spheres, my surface area becomes smaller, right? So I'm able to achieve a larger volume with a smaller surface area. This is another thing that we need to remember. So if I start with a larger initial sphere diameter, right, A, I will be able to achieve a better packing efficiency, and B is that my total surface area that I have to deal with is going to be smaller. Two things that we have to bear in mind. And of course, the aggregate that we are typically dealing with, we are classified in IS 383, which is the parent code for aggregate. Right? Here we break them up into two sizes. The coarse aggregate, which are basically the larger aggregate, which are either crushed stone or gravel, or uncrushed stone or gravel. The uncrushed stone, the nice smooth stones, have now disappeared. Most of our aggregate is coming from crushing, which is a very violent operation. And basically what we end up with something which has a very irregular shape, rougher surfaces, and this is what we have to deal with. So where are spheres and where are these particles, right? But whatever we learn from spheres still teaches important lessons. And those lessons that we learn from packing spheres still carry over here. And that is important to remember. Now, grading, well, ASTM, this is a curve from ASTM where they basically give two bounds, upper bound and a lower bound. And if your aggregate size distribution, the particle size distribution, fits between the upper and lower bounds, we consider those aggregate to be well graded. What does that mean? Well, if they're well graded, we expect that the proportions are available in the, or the sizes are available in the right proportions. I expect that packing is going to be good at some level. Now, why is this not precisely a line? Why do I get a band over here? The reason I get a band over here is because I'm not dealing with spheres. These are irregular shaped. So, and every time I crush aggregate, I'll get a different shape distribution. It's not going to be the same. And remember, packing game is all about packing the volume. So the shapes matter. So I cannot give you a precise mathematical relationship. What we typically give you are these bounds, upper and lower bounds. And we say, well, if it fits in those bounds, we expect the aggregate to be well graded. IS 383 gives us similar bounds. We basically have, depending on the largest size we start with, we get these bounds that are given, and we say that, well, if it fits between those bounds, then we have well graded coarse aggregate, right? Again, just to reiterate, what do I expect from well graded aggregate? I expect them to pack well, right? The next size, fine aggregate. Okay. Now the question is, why do I need two classifications of aggregate? Why do I need fine and coarse? Remember, it's all about packing. Okay. If I only use one size sphere, there's only so much volume I can pack. How can I pack the remaining volume? I need to bring in smaller aggregate that will go and sit between the gaps between the larger aggregate. What are those fine aggregate? These are the fine aggregate, right? So what do we call our fine aggregate? It is anything that is smaller than 4.75 millimeters, right? Or majority of it, but for 5%, passes through a 4.75 millimeter sieve, is called a fine aggregate. Previously, we used to get this naturally available sand, which we used as fine aggregate. This has become a luxury, at least in the southern states. We don't get this anymore. In the northern states, perhaps sand is still available. Not sure, but I think it's still available. What we are making do with is this crushed aggregate. So what do? We go back to the crushing process which produced coarse aggregate, only crush it finer, and then call it fine aggregate. But the game is the same. What I want to do is achieve maximum packing. So look at packing of the coarse aggregate. After I'm done with the packing of the coarse aggregate, there'll still be a lot of gaps left between the coarse aggregate. And those I hope to fill with this finer aggregate. Right? Now, when it comes to fine aggregate, this is how 383 deals with. We actually put it into zones. Now, the question is, why put it into zones? Why not deal with it like we did in coarse aggregate? Why not just have one master curve or something which says, if it passes this, then it is well graded? Now, the reason for this is that a lot of times when it comes to finer size particles, it's very difficult to precisely control the size distribution. I cannot really precisely control how I'm crushing it. The second thing is the origin of fine aggregate. It started as naturally available sand, in which case I had no control over the size. Whatever I got naturally, whatever size distribution was available, I used it. So in that case, then it was convenient to basically put it into one of these zones, right? Now, why these zones are important, I'll explain in the next few slides. So the whole idea is, if you take fine aggregate, you basically try to see which of these zones it fits into based on its size distribution. And basically, we have these 4 zones that go from 1 to 4. And if the fines are increasing, the fine content is increasing, basically you're going from zone 1 to zone 4, right? It becomes finer and finer as you step into zone 4. Right? So when it comes to coarse aggregate, we insist on some size distribution because at some level I can control it. I'm crushing it, I control it. Right? This invariably, if I'm dealing with naturally available material, then there's only so much I can do to control the size. So I live with it. What do? I say, well, I'm going to put it into a zone. And what is the game that I'm playing here? It's always about packing. Remember that. Right? So this is the game that I'm trying to play. Okay, so if I take, let's say, coarse aggregate and fine aggregate, again, whenever I illustrate, I go back to spheres, knowing full well that This is not reality, but the lessons I learn here can be ported into my real life. Now, what would happen if I try to pack coarse aggregate, which are well graded supposedly, with fine aggregate, which have their own distribution? Well, if I try to pack them up, I expect the smaller aggregate to go and pack between the gaps of the larger aggregate. And that's a winning game for me. So if I look at percentage of voids, and let's say I start with naturally crushed aggregate, this will start decreasing as I increase the percentage of sand up to a certain point, right? It'll hit a minimum and then it'll start increasing again. So what happens after this point here? I've achieved a minimum. I cannot give you a mathematical description of this fellow. I mean, I cannot tell you just by looking at it, okay, this is the mathematical equation you can use to come to this number here. It's empirical, right? I come up with this from experiments, from experience. But I know the fundamental theory is this, which comes from spheres, circles, which I can describe mathematically. So, and then after a certain point, what happens if I keep on increasing the sand or the fine aggregate? It starts making space for itself. And in the process, what happens then? The void percentage increases again. So there's a certain minimum that I get, right, of the percentage of voids, which when I have the right proportion of coarse and fine, right? And that minimum percentage would depend upon this crushed aggregate, what I'm starting with, and what I'm filling it with. Okay. So coming back to the packing models, I'll describe how this plays out in the code a little later. The spherical packing models would help us understand the basics, okay, as to what is the cause and effect. Okay, we've understood two things. One is, if I want to make an informed choice about packing, I have to go with hierarchical packing. That is, I cannot go with spheres of one size. I need to stack my sphere sizes. There'll be a certain optimum. If I overdo it, not going to help either, right? Then maximum aggregate size plays a role. How? If I start with a larger initial size, I hope to hit a larger volume of solids, which means I improve my packing density. And that knowledge I gain from playing with spheres is going to be smaller. Now let's see how this plays out in our IS 10262. Packing is addressed in this table here. We don't realize it, but it's built into the table. How does it play out? Well, here what we do is we decide the proportion of coarse and fine aggregate, right? So if you look at it, starting with the nominal maximum size of aggregate, you presume that these aggregate are, which are coarse aggregate, are well graded, which means they themselves pack well. Okay. Suppose I start with 40 mm size and I'm given zone 2 sand, then I know 0.71 would be the volume fraction of coarse, which means 0.29 is the expected fine that would give me high packing, right? Now, why is it given in a table form? Remember, this fellow here, the fine aggregate, is not in my control. I get some size distribution. So what am I trying to do? I pack my coarse aggregate, then bring in the concept of hierarchical packing, pack the gaps between the coarse aggregate with the smaller sized fine aggregate, and I've come up with this table here. Okay, but this table is empirical. Nobody can derive this table from you. The lessons to take here are coming from what we learned from the spherical packing models. But this is built into our code, where basically the whole idea is that you want to pack as much solid in the form of aggregate as possible in your concrete. Okay. Now, this is typically how it plays out. That is, if I actually look at the maximum aggregate size, you look at the percentage, this is the total volume. You see that I can actually increase my aggregate content in the concrete, decrease the paste content, starting with a larger aggregate size. Now, you may be wondering, where the heck do you even see something like a 150 millimeter aggregate, 225 millimeter aggregates in dams? Okay, even in highways, it's not unusual to see a 45 millimeter or even 75 millimeter aggregate being used. Okay, so what am I gaining with a larger sized aggregate? Larger volume of aggregate, smaller volume of paste. Then why is it that we don't use this in our normal construction? Most normal construction is done with this fellow here, which is 20 millimeters. Why? Sorry? Because we have to fill a form. Most of our form structural members are slender, or they're basically thin. And if I consider a 200 millimeter thick web or of a beam and try to force fit at 150 millimeter aggregate, it's just not going to go there, right? So I have to pack it. That's the reason why we are sliding down this here, because we are making our members smaller, thinner. So what happens then? We are going down this path. And as a consequence, what's happening? Okay. Now, think about what we are doing in printing. Typical nozzle size is 50 millimeters. So what? You think this will work? Even that is too big. So what happens? Now I start coming down here. Then what happens? The paste content goes through the roof. And that is reality. What we're using as concrete and printing has a very high paste content. Okay. Right. Now, last few slides. So let's look at what happens when concrete is at rest. Let's try to understand what a slump and that third lever that we haven't pressed so far, which is aggregate. We've understood packing. We've understood strength. So I'm going to adjust the water to cement ratio for my strength. Packing for economy, right? So that I use minimal cement paste, and we follow a certain packing procedures that come from packing, right? The other thing now is concrete at rest. Where is it at rest? How do we measure it? When I measure a slump, it's at rest, right? So, so if I look at concrete now, going back to my basic definition where I said these are aggregate, this is cement paste. What happens in reality is when you mix the concrete, the aggregate get coated with this paste layer. There's a thin layer of paste that forms around the aggregate, right? When you whip this aggregate in mixing action, what happens? The aggregate are churned along with the paste. So all the aggregate get coated with a layer of paste, just about a fraction of a millimeter to a millimeter thick. Now, this paste layer will always be present on the aggregate. So why is that important? Well, my paste demand increases with surface area. So if I now give you concrete which has a smaller, largest size, what will happen? The surface area would go up, which means my paste demand would go up, right? So if I'm trying to balance packing and the paste demand for whatever reason, then I have to expect this. Now, where is the paste demand important? So when we look at concrete at rest, so we know the slump test. Follow the sequence. We fill the cone, we pull the cone out, it comes to rest in this position. Suppose I was to take a snapshot of this here. This is what it would look like. Going back to my fundamental definition again, these are my aggregate. Now these aggregate are coated, right? This is that film of paste that's formed around the aggregate. They're sitting in a paste medium. This gap, it's not like there's air there. This light gray here is the paste, right? Now, if I now look at these aggregate, it looks as if these aggregates are precariously perched, right? Something is holding them there, otherwise they'd simply slide out, right? Now, if you look at this, what's happening? You have essentially this paste layer that's between the aggregate, right? Now, if you look at the stress state on this paste layer, what would you see? You would see actually that the paste is subjected to a shear stress, right? Now, what would happen if this paste had a high yield stress versus the paste has a low yield stress? What do you think would happen? If this paste has a high yield stress, it will be able to withstand a higher shear stress, right? Which means it's going to hold this aggregate in position and allow you to create a larger height in the slump. What happens if this yield stress is low? It will simply shear off. So what will happen? This configuration will not be possible because internally the fluid, the paste cannot sustain that level of shear. It's going to give way, it's going to slip, it's going to shear off. And what will happen then? The concrete will settle even more and you'll get a higher slump. So what ultimately determines the slump of concrete? In addition to all the other factors that we have, yield stress of the paste. Okay, remember, because this is again a static condition, it's not a fluid condition, it's not a flow condition, right? So now coming to fluidity, how do we control the fluidity? Remember that these aggregate are coated with a layer of paste, right? And it is the paste content that controls the fluidity. Now, the way that the code controls this is by regulating the water content in the concrete. Okay, there's a table that's given here, and this table is based on what we call the paste demand. Paste demand for what? Paste demand to coat all the aggregates, right? There's a certain minimum amount of paste that's required. If I go below that, I will not have enough paste. Now, the way the code regulates it is by the water content. They stipulate water content which varies with the aggregate size. And you notice what happens here. When you go from 10 mm to 40 mm aggregate, the water content requirement actually decreases. Why? Surface area. Okay. So the effect of surface area is built into this table 4 of the code. Okay. Intuitively, we should know that this comes from packing the theories that we learned from spheres. Okay, although we are dealing with irregular shaped aggregate. And there's an elaborate explanation of that, which says that basically water content is influenced by a number of factors. They always try to hide behind a lot of factors, but most important factor is the paste content. And what controls the paste content? Because you're already stiffening up requirements on cement and other things. So basically, they're regulating the water requirement here. And basically, an increase in the aggregate size will reduce the water demand. Water demand for what? Flow. To induce a certain flow behavior of concrete. Why? That is controlled by the paste content. Okay. Now comes my last lever that I want to press, which is I've done everything. Now I want to control my water demand. That is, I want to make concrete flow with less water because I have other constraints, right? If I try, there's already a limitation put on the cement content. I want to achieve a certain strength, which means I have to use a certain water to cement ratio, right? Even if I maximize my cement paste content in there, the paste itself has a very high yield stress. So what will happen then? If the paste itself has a very high yield stress, this is what I end up with. It's not going to slump, right? So when I lift the slump cone, basically it sits in the original shape. How is it able to keep the shape? Between the aggregate, the paste has such a high yield stress that it doesn't shear off. It's going to hold on to that to the aggregates in the position. So you end up with a nice stiff concrete. How do I get this thing to flow? I've already pressed all my levers. Here come the admixtures, right? So I can basically use an admixture, right, to reduce the water demand, right? So I can basically maintain the same slump, okay, with a lower water content or increase the slump, right? Basically, what am I doing? I'm artificially playing around with the demand of water for a specific requirement, which is flow requirement. Right? If I take regular cement paste, suppose this is the yield stress of the cement paste, what would happen if I added a specific admixture, which is a superplasticizer or a high range water reducer? What does a high range water reducer do? What does a superplasticizer do? It reduces the yield stress of paste. It doesn't affect the viscosity, it reduces the yield stress. So what would happen? Remember this curve here? Yield stress of the paste would drop if I added some admixture to it. And my concrete would basically start flowing. I've not increased the water content. I've added an admixture. Small quantity that changes the flow behavior of paste. Suddenly now, my static condition, this is favored, right? If with this yield stress I was to achieve this, this will not happen. Why? Because in this configuration, the shear stress between the aggregate, the paste cannot sustain it. It will just simply shear off. Now, another condition of rest, which is what happens when we vibrate it. So we're dealing with concrete that looks like this. The minute we apply vibration, look what's happened. It just flows like a fluid. So what changes there then? Again, it was at rest. If you look at it, I just agitated it. So what happened when I agitated it? Well, let's see what we get with. So I'll just play this video again just once. Right, so this is concrete and then it's being agitated. Suddenly you find that it becomes fluid, it flows and it fills the form, which was our basic definition of workability, right? So why would that change? Going back to my static condition here, this is an aggregate covered with the paste layer. Now, what happens when I agitate it? The aggregate will have relative motion. All the aggregate will try to move relative to each other. Each one of them is moving. What is happening in the process now when I've agitated? This paste layer between the aggregate is getting sheared, it's getting agitated, right? It's getting sheared, okay, in a dynamic condition. So what kind of condition am I creating in the paste layer here? It's like a dynamic condition, right? Now, going back to the basic rheology of cement paste, what did we expect from cement paste? It had a yield stress, right? That was when it was at rest. That's what gave me this shape here, right? That was this fellow. The minute I agitate it, what happens? Now I'm introducing a gamma dot. I'm trying to basically produce a dynamic state. So what happens? This is shear thinning liquid, right? It starts loosening up. And that basically starts producing this relative movement. It flows really easily, fills the whole form. Okay, so this is the role of vibration. Okay, and in some sense, if you really understand this, cement paste is our friend, because the yield stress is what gives me this, allows it to keep that shape in a static condition. It is the once it starts to flow, the more I agitate it, the easier it gets to flow, right? And that property I use when I'm trying to vibrate it and fill my form, right? The last thing I want to talk about is pumping. What happens when you're pumping aggregate, when you're pumping concrete? So when I pump concrete, all these aggregates are making a mad dash. They're rushing through. They're being pressurized from here. And I'm applying the pressure on the aggregate. I'm not on the concrete. I'm not applying it on aggregate itself. So I'm trying to force this entire concrete through a pipe. What happens there then? The aggregate, basically, each person for himself. What is happening? The aggregate are trying to move whichever way is conducive for itself. What forces the flow of the aggregate? What are the stresses? And the aggregate tries to minimize the stresses on itself. That's what it's trying to do. In doing so, suppose this is the flow of concrete and the aggregate are all moving relative to each other. Okay. Now, the aggregates are all coated with this layer of paste on them, right? And as I'm pushing this, what's happening? The paste is also trying to move through these gaps between the aggregate. How can I get this whole thing to flow properly? Well, I have to facilitate movements of this aggregate, which means the rheology of the paste becomes important. And I have to allow some extra paste so that that paste can also move quickly. It's like a lubricating layer between this aggregate, which also will basically flow through the between the aggregate and facilitate the movement of the aggregate. Remember, the aggregate flow is in this way. What do I mean by saying aggregate flow? If you look at the aggregate as a bunch, as a whole, there's a total movement in this direction here, right? And individually, the aggregates are also moving relative to each other, right? And there is also movement of paste here. How can I make this job easier? Well, I can make this job easier, and this is actually codified, which says that if you actually have concrete that is to be pumped, increase your paste content by 5 to 10%, or decrease the coarse aggregate content by 5 to 10%. Why? So you increase the paste content that allows for this movement of the paste between the aggregate. Okay. So basically, this is the fundamentals of concrete mix design. We play with our aggregate, content, packing, paste content, composition of the paste, how much water to cement ratio. When all else is done, bring in some admixture to control the final outcome. Right? And fundamentally, it is the rheology of the paste that determines the rheology of the concrete. In what sense? If the yield stresses of the paste is high, we expect a high slump from concrete, which means it is able to hold level differences much easier. It starts behaving like a solid. Higher the slump, what happens? That means it's going to flow more. Right? That is our understanding. Right? Um, and we have to have enough paste to coat all the aggregate. And that's a game that is played by the surface area. Okay. All of these things are built into our codes, although in empirical forms, because exact mathematical definitions cannot be developed for something that is not spherical. Okay. So final, when all is said and done, this is typically what we end up with in concrete. We have coarse aggregate, pack the gaps between this with fine aggregate. Then we have cementitious material that go and pack the gaps between these two. The whole objective is to minimize this content here, to bring down the cost and maximize these fellows in order to achieve better economy. Okay, so I think that is my last slide. I went probably 5 minutes over, but probably open the floor for questions. Any questions at this point of time? Yes, no, maybe early in the morning. Sorry? Slump and yield stress relationship. Okay, fine. So you understand what is the yield stress of paste, right? At some level, we say, well, it is that initial resistance to flow. Unless you overcome the yield stress of the paste, it's not going to flow, right? So now what I have is, suppose I go back to my this here, right? So this is, now I'm looking at the concrete scale. Now at the concrete scale, I'm looking at aggregate, which is coarse and fine, with paste in between. And when I fill the slump cone and I pick up the cone, what happens? It comes to rest in this position, right? Now, suppose I take this fellow here, some part of this, and zoom into this. What do I see? I'll see an arrangement of aggregates. These are in a static condition. Somehow they are holding their position. And I have paste filling the gaps, right? And it's not like this deeper color here is a different paste, and this is the same paste. It's just that I've demarcated that coated aggregate with that deeper color. Now, if you look at, let's say, one of these aggregates and you pull it out and look at the what is happening on the aggregate, right? That aggregate is in a static condition, right? There'll be forces that will be pushing it out of position, right? But somehow it's able to hold on to that, right? Then if you look at, let's say, two aggregate contact, what's happening here? We have the liquid here, which is the paste, right? And that would be subjected to a normal stress, some normal stress, because the aggregate will be in contact, right? And there'll also be some shear stress that would develop there. Okay. Now, what prevents this aggregate from sliding in this position? It's if this fluid here is able to withstand a higher yield stress, it's going to block that in place. It will not allow it to shear. Okay. If that liquid had a low yield stress, what will happen? The minute I apply some shear stress to it, it will shear, it will flow. It will not allow the aggregate to be in this position because it cannot withstand that much shear. Okay, so what happens? Then the aggregate will move, continue to move, right? And they'll find a more favorable position, which is not possible with that. So then it basically, the slump then increases. Okay, so if I increase the yield stress of the paste, I expect a smaller slump value. It will not slump as much. Then I should be able to keep higher level differences in concrete. It starts behaving more like a solid. Why? Because what it takes to induce flow in cement paste, that stress is very high. Okay. Admixtures will not reduce the viscosity of the paste. Only one super plasticizer, as we call it, or high range water reducer, is designed to reduce the yield stress, not the viscosity. Okay. And there's a lot of confusion here, but high range water reducers are intended to reduce the yield stress of the paste. Okay. If they happen to reduce the viscosity, and they don't reduce the viscosity, but if they happen to change the viscosity, it's an unintended consequence. That's not what they're designed for. They are not similar, right? Viscosity is after flow starts. Yield stress is while it is static. Okay. So what is yield stress? Suppose I take a fluid, apply some shear stress, low value of shear stress. It will be able to sustain that shear. It will not flow. It will basically remain static. Okay. What is your viscosity? Once I overcome that initial resistance, once it starts to flow, the resistance to flow is viscosity. Okay. Two very different things. Right. Any other questions? Yeah. Efficiency with spheres, you can play these games. I think numbers are there. Like there are enough mathematical theories where you can maximize it. Okay. But when you deal with irregular sized particles, sky is the limit. And when I talk to people who work in packing theory, and I said, look, we are able to hit 80% packing and get only 20% even with normal concretes. They're shocked because achieving that with spheres is very difficult. Spheres are notoriously difficult to pack. When you start dealing with irregular shaped aggregate, sometimes you get much higher packing efficiency than you would get with perfect spheres. Okay, so when you're dealing with irregular objects, yes, that we mostly rely on empirical packing rules, right? There are certain theories, but then we use them as a guide. Some level of trials have to be done to basically match, because um, exactly spherical theories would lead us in a certain direction, which are pointers. And then when we're dealing with actual powders and actual particles, which are not exactly spherical, we'll have to do some trials and exactly try to fit it to that. It will not be exact match with this. Well, you're getting into UHPC domain. So I'll park that question here. It's not directly relevant to what we're doing. Yes, it is an issue. And UHPC has been shown to be to fail in a lot more catastrophic manner under fire. So yes, that is a concern. But I wouldn't blame the packaging for that. Okay, it's just that particular brand of concrete UHPC, which is packed to such an extent, and you have very high cementitious contents, and all these factors combine to give you that kind of a response, specifically in UHPC, not in all other good, well-packed concretes. Okay, right. Any other questions? Absolutely, absolutely. That's where, if you read IS 10262, it says, please do your trials. They only give you guidelines. They'll say, look, that all the tables, charts, they'll say, look, this is rule of thumb, a guideline, but you do your own trials. Okay. And that's because the code is, or they're smart enough to realize that aggregate from quarry to quarry, they'll vary in surface area and particles, shape, sizes, everything. So yes, developing exact science for that is not possible. We cannot develop an exact mathematical relationship. This is just a heuristic or a simplistic understanding of this. This is what I expect, I should say. If I decrease the yield stress of the paste, I'll expect it to flow better. I'll expect it to come to rest in a static position, which has lower shear stresses in the fluid. It's as simple as that. Okay. All right. I think, yeah. Correct, yeah. No, remember the three boxes that we had, right? The very first one was strength and durability. That was for hardened concrete. That is never to be compromised. This is the flow behavior. Okay, so whatever I do here should not affect that. And remember, how do I grade my concrete? It's in some M gradation, isn't it? M30, M35. That is strength. 28-day strength, hardened strength. This is the games that I play when it is fluid, when it is plastic, and all that. Right? All three boxes have to be ticked. Okay, and I have only so many levers in my hand. I can control the water content, I can control the cement content, the aggregate content, and the breakup between coarse and fine. Right? And then if all else fails, I bring in some admixture to help me a little bit. Okay, but yes, you cannot compromise on that strength or durability. Those are the hardened properties. Okay. All right. So I think if there are no more questions, I'll stop here. I think I've